All right, everybody, it's 10 o'clock. I'll give it probably a little bit of a time here. Let another minute tick off the clock just so that we have the people joining in the call have the ability to hear the plan for the day. But maybe I can go ahead and introduce myself. My name is Daniel Thompson, and I'll be your host on today's webinar. And I'm pretty excited. We have a good panel for you guys, collaborators in the direct current space. So for those of you that are new to Current OS webinars, welcome. Thank you for coming. For those of you who have attended past Current OS webinars, you'll notice that we've had a lot of comments about how the webinars are very Eurocentric, and that's understandable with Current OS being established in the Netherlands and Europe really having a head start on DC microgrid standards. But we've had a lot of feedback from people that they'd like to understand more about what's going on in North America. So we thought, well, wouldn't it be great to have a series of webinars that are North American focused? So this is the first in that series of webinars, and we're really excited to talk about things here. In this particular case, our pilot project that we're looking at is in Raleigh, North Carolina, and we'll talk more about that as we move through the webinar. But for now, I'm just going to welcome Sean Burke from Intelligence, Chris Savanich from Schneider Electric, and Travis Owens from World First Solar. And we'll talk a little bit about Current OS. But before we do that, let's just set a few ground rules. If you have questions, it's great. You can ask them at any point in time. Please put them in chat. And when I get to the Q&A section, I'll go down any questions that may be in the chat at that point in time. We will be recording this webinar for people to view it later. If you'd like a link to the webinar, you feel free to reach out to us and we'll have some contact information for you to receive that webinar link if you want to share it with other people. And then don't forget to follow Current OS on LinkedIn. We also have a great set of YouTube videos that are primers on basic concepts around DC DER connected systems or DC microgrids. So Current OS is a few things. We're a global foundation for the advocacy of direct current microgrids. But we also published a design reference guide, and we work across industry, collaborators, competition, collaborating together on various aspects of load and source management and other principles. We're leading research and innovation partner, partnering with both academic stakeholders and manufacturers to advance the topics surrounding direct current microgrid. And we're really, we view direct current as the disruptive power management solution. So by giving some standards to the topic, we allow people to have a level of interoperability that is unparalleled right now in industry. So we have just welcomed, as of this morning, our 91st. Didn't get a chance yesterday on my slide with 90 partners to update the logo, so it's a little bit of a Where's Waldo game for you guys if you're watching this on the recording. But we have our 91st partner joined today, and we have a global span of technology providers that are all working together. You'll find on the Current OS website, we have many reference projects located around the world, and we'll be continually adding to this group of reference projects that you can click on and drill further into the details of these exciting and innovative projects. So for the panel, we're going to start off today. I'm going to ask a few questions. I just like to hear your guys' thoughts on the questions. The first question that we have today are, what are the biggest challenges facing energy users today? And maybe we'll direct this question to Travis first. Sound good, Travis?
Yeah, thank you, Daniel. Let's see. So many of the challenges that I've really seen have stemmed from the instability and unreliability of the current US grid infrastructure. You have capacity limitations, which lead to blackouts and conservation efforts. You continue to see across the board rising energy costs, demand charges, and even other tools used to minimize the effect of capacity limitations. And on top of that, you have extensive lead times on transformers and other electrical upgrades, as we try to keep up with the rising demand for energy needs. And another challenge that we've really seemed to face on the renewable energy side is conversion losses. You're constantly converting from DC to AC back to DC power. You produce DC power through solar. Many of your electrical appliances are DC based. There are just a handful of obstacles that are currently prevalent for energy users today.
Awesome. Thank you, Travis. Chris, do you have any thoughts on the topic?
Yeah, I'd like to I could kind of give an overview here of the current state of energy and what's been happening here in the U.S. and within North America. Happy to get into that, Daniel. Thank you. So as Travis said, that we've seen an increase in energy costs. And it's been pretty substantial on average in the U.S. over the last 2 years. On average, a 65% increase in energy cost. And previously, I'd say the last 10 years, we had pretty cheap energy. Most of it came from coal, and then the transition to natural gas, and natural gas from shale fracking, and so on. And because of that, the U.S. was able to enjoy a fairly low cost of energy. But now that cost has increased, and it's increased because of the way that the utility rates are designed. So here in the U.S., the utilities have a unique way of earning their revenue, and it's through the kilowatt hours, people consuming energy, but then it's also based on rate recovery. What that means is every time that a utility goes and deploys capital, so it could be building a coal plant, building a solar field, putting a pole in, putting a wire in, transformers, they earn a set rate of return by the state regulator, and it's on average about 12%. So every pole that goes in the ground, they earn a 12% return on that asset for a number of years. Since we have, as Travis mentioned, he talked about the aging grid, we have an old grid here, right? When you have utility poles that are 60 years old, they need to be replaced. As we transition to away from coal to other power plants, whether it's natural gas and or solar and or wind, there's costs associated with that. So as that more and more capital is being deployed, the utility then are earning that 10, 11, 12% return, that rate recovery then on all that capital that's being deployed. So it's gotten expensive. That's the bottom line, right? Our current state of energy has gone up, and everyone feels that. The next piece I'll comment, I heard Travis talk about the grid stability and reliability. There was an interesting study that was done that identified that 35% of large commercial and industrial users receive momentary outages weekly. That's a pretty big deal. And I think the reason for that is because we've become more sensitive to power disturbances. Because I remember 10 years ago, we'd have an issue. It would be an outage. It could be a couple seconds, maybe a minute. No, not a big deal. We went back and we continued our operation. But now with all of our sensitive power electronics that we have, not even seconds long, but millisecond dips in the voltage from that utility, it's very disruptive to the manufacturing process, to an assembly line, to some type of fabrication that's being done. So that's why we've seen now an increase in the amount of reported momentary power outages here in the U.S. The next piece, Travis said about the capacity constraints. That's real. On average, Lawrence Berkeley has published, they said it takes 24 months for utility interconnection. What that means is for having some type of asset being tied to the grid and getting that approval, or getting the necessary equipment that's needed in order to do that upgrade. So typical process, somebody wants to go and install some solar, maybe EV chargers. They look at their existing infrastructure, that they have to upgrade any of the switchgear or the transformer. They work with their utility. Their utility does a couple studies, a short circuit study, a load flow study, and then they're able to determine what upgrades need to be done to the system in order to support that load. I mean, I remember working recently on a small project in Detroit for a small number of EV chargers and a little bit of solar. It's 18 months, and they still don't have the interconnect, which it's unbelievable, right? But we saw it happen in other parts of the world, and now we're seeing it here in the U.S. with that real constraint. And then the last piece, our electric demand is growing. There is the shift from using natural gas for heating going into electric. We have a lot of data centers going in. There's a lot of data centers that are going into the U.S., but also a lot of manufacturing. We see a lot more onshoring of factories. Those are big loads. People are using more energy, right? And as we do that, that's increasing our demand. And plus the electrification of fleets, transit, they're all in, they're electrifying, and we're expecting a 3x increase in demand. That's a big number, right? Not 30%, but 3x. So what's happening is we have an energy transition taking place. We've seen it in other parts of the world, right? We've seen it in China, we've seen it happening in Europe, and now it's happening here in North America. And I think energy users have taken that step back and go, well, wait a minute, we've got real issues. Those real issues that I just talked about. And what they're looking for now, these energy consumers previously are looking for, I need power, right? I need a certain amount of MVA from the utility for whatever we're doing. If we're building a new facility, if we're expanding our facility, maybe we're putting EV chargers in, whatever the case, we need power. We need it to be available. I need it, in a reasonable amount of time. I can't be waiting 2-3 years for 1 MVA. That's just not acceptable to where we are in a competitive business environment. And it's got to be reasonable. The cost of energy is, as I said, on average 65% increase. It's got to be reasonable cost. And then obviously sustainability, especially for any publicly traded firms, sustainability is very important. So those are the goals today of energy consumers. And now they've looked at, I got all these real problems. How do I solve it? And that's where DC power distribution has been a solution. And what's been happening now is people are becoming, instead of a consumer of energy, they're becoming a prosumer. This is allowing them to produce their own energy, regain control over their energy usage. So now they're controlling their lead times. They're controlling what that cost of energy is, which is both from a capital intensive standpoint, CapEx, and then also an OpEx, or ongoing operations cost, price per kilowatt hour. And they want it simple. I'll tell you, that's a real big issue. When anytime somebody does any type of project, make it easy. And I think you even can reflect on it personally. If you're about to go do whether a project, or you're working on something at your home, or you're gonna work on something with a group of friends, you want it to be easy. Nobody wants a real hard project that's going to take a lot of time to be able to do. You want to make it simple, and that's what DC's been for us in the U.S. here. What we've seen is it's really been that tool to help us through that energy transition, to give us these benefits of a lower cost of energy, being able to do it much cheaper, to deploy it, and then a much simpler system. And this is the example of the system that we deployed here with our partners here with World for Solar and Intelligent. So the system that you see here, this is a carport solar system. What's been really nice about this system, inside of it is the battery energy storage system, as well as the EV chargers. What's really impressive to me, for someone who's been in the energy space for over 2 decades, if you see on here, we talk about from the design to the deployment, meaning design, right? Start of engineering design, procuring the equipment, installing it, commissioning. That was done in 8 weeks. That's super fast, right? Especially from what anybody here who's worked on a project, from an AC interconnect standpoint. I mean, you could spend 6 weeks on engineering design on an AC side. So being able to do something using DC, using current OS as well, was the basis here and the foundation that was used to put this system together. And I'll show you a little bit more more details here on this system. So the big issue for when we went and deployed this system, this one was done actually in Raleigh, North Carolina. It's a site that you can come and visit. We found that it was much cheaper in a CapEx standpoint compared to an AC coupled system. Part of it was in the wiring. We found that to be in the wiring, the conduits. We also saw it from equipment upgrades of electrical switchgear. So being able to minimize those aspects was able to help save in the CapEx. We heard Travis mention earlier about the efficiency piece. That's a big deal. These diagrams, I think, are pretty nice. You can see an AC system with a bunch of AC to DC converters. You lose a lot of efficiency there. And then in the diagram below, a bunch of DC equipment, all DC to DC converters, much more efficient. Now we don't have as much losses, so that helps with the OpEx piece, right? So now we're not losing as much energy from the system that's being able to produce. That also helps from a sustainability standpoint. The system itself has less embodied carbon, but then it also produces, or when we're consuming energy, we're also consuming less kilowatt hours of energy. So when we look at these types of projects, one for this carport solar and EV charging type solution, or even when we do other projects, we've seen on average between a 26 and 50% savings in the CapEx. That's a pretty significant number, and that really varies based on what does the installation look like. Is it a bunch of EV chargers, and that's all on a DC bus, or is it something with this where we have solar coupled to it, or is it something where a battery is connected in as well? And then we've seen a range between 5 and 16% on the efficiency, the energy, minimizing those energy losses compared to AC. Those are significant numbers, and I think that's the big difference. I think of what we've seen here with DC using currentos compared to an AC system, is that's really given us that exponential step here of improvement that the whole industry has been looking for a number of years. And I have my contact information for you here, so if anyone who wants to reach out, feel free to in the future here. Thank you.
Thank you, Chris.
Back to you, Daniel. Yep.
Yeah. So I can definitely understand, taking 8 weeks on a project just for design. I've seen that happen over and over again. But I wanted to ask a question to the panel. Why is DC power distribution not more common? Like, if this has been such a great idea, why aren't we seeing this more? And maybe if I can direct that question to Sean to start off.
Yeah, that'd be great. Yeah, and this is a question that we get all the time. Is like, if it's so great and you could save so much money, why am I not seeing it more? And the thing is, we've all grown up in an AC world and that has been taking effect and building out infrastructure for 100 years. So AC has been kind of the status quo. DC is new. Now, even though conceptually the idea of DC and DC microgrids have been around for some time, the products have not really evolved until really the last decade and really over the last few years. They've just not been available. But the reality is now, when you look at all the devices around us, computers, mobile phones, our LED lighting, EVs, solar, so our clean energy, it's all DC. And in fact, we live in a DC world, but we still have the remnants of the architecture of AC, and we're going to be moving towards DC in a bigger way. It's not going to be overnight, but as we hit new products and also the standards, because a lot of our standards, safety standards, regulatory standards, have been really oriented towards AC. Now we're developing more of that for DC, and as a product development company, these are good because it gives us kind of the boundaries of what we need to develop products to. And currentos is one of those really, I think, foundational standards that really help drive this. And now we can be really focused on delivering better products that are kind of within that standard.
Awesome. Thank you, Sean. Travis, do you have any thoughts on the topic?
Yeah, kind of leading off some of Sean's points. I think some of these challenges from the historical standpoint of the AC grid aren't necessarily the case as DC rises in popularity. You're seeing many of the data centers, renewable, all moving towards DC for efficiency purposes. Long distance, high voltage DC is now starting to become the preferred due to the lower losses within it. And so I think it's the next transition as we, move towards, more of a standardized DC solution.
Awesome. Hey, Travis, why don't you step us through your part in the solution?
Yeah, absolutely. So, my name's Travis. I work for World for Solar. I want to tell you guys a little bit more about the product that Chris was showing you off of the case study that we built in Riley. So, what we really wanted to achieve is a scalable DC solution for solar, EV charging, battery storage that can truly be implemented in real-world scenarios. Anyway, the next one. So, we highlighted some of these, opportunities and challenges in the first question, but there are a lot of opportunities and challenges that we still have ahead in order to get the DC's, energy more effective. We are constantly seeing increased demand for renewable energy, for resilient EV charging, for microgrids and battery storage. And yet, at the same time, we have a lot of infrastructure challenges associated with it. As Chris was alluding to, we're seeing up to 5-year timeframes to get large-scale projects online. And at the exact same time, we're expecting to see an 18% plus increase in power demand over the next 10 years. This leads to, energy constraints unless you can really find a scalable solution that can be quickly deployed. Otherwise, it's just going to continue to get worse. So, in coordination with the current OS guidelines and Schneider Electric, we developed the Lumaport DC solar carport with DC EV chargers and high voltage batteries. The objective is to have a completely scalable system in segments that avoids any sort of customization process. It's durable enough to withstand the harshest US conditions, even if you're putting this into the Miami-Dade County. And it's designed where all of the components are completely hidden inside of the structure itself, allowing it to be deployed directly to the site as a standalone microgrid that avoids any energy conversions. Yeah. So why did we standardize on current OS? We wanted to design and build a DC system that eliminates conversions and waste, and that can combine, solar PV, battery, EV charging, and bring standardization to the DC energy field through the current OS guidelines, which I think is part of what has hurt some of the expansion of DC energy over the years in the US. Yeah. So how does it work? Chris showed a slide. Essentially what we're showing is 2 of our columns. This can be scaled out to as many as you would need. And then the solar array would be on the top that you're not seeing. So essentially you produce power in DC through the solar modules, and it goes to a 700 volt DC bus that is droop controlled. And then from there, it can either be transferred directly to high voltage DC batteries to be stored, or it can go directly to a DC compatible EV charger. And then from there, you are able to transfer it directly to, electric vehicles into their battery. It eliminates any conversions throughout the entire process and significantly reduces, any sort of energy losses through the stages. So what are some of the benefits? You can monitor and control the system in real time with the multiple columns all being independent but still connected. You can get load balancing between the columns and pull the battery storage where is needed. So if you have, 10 EV chargers on 10 columns and only 5 of them are being used, you can pull the excess energy from the other columns in order to meet the demand of the EV chargers that are currently being used. So it's entirely scalable solution and really solves a lot of the problems that the current grid has today. So we recently were working on a case study, and as counties and states, work to fully electrify their commercial vehicles, we looked to develop a solution that can bypass many of the current energy challenges. So we're working with the school district that is moving towards a completely electric fleet. And the objective of the design is to be able to charge all of their electric vehicles without having any sort of capacity issues and allowing them to charge those vehicles on a fully contained microgrid system. Going back to Chris's point, in order of doing this, we don't need to upgrade all of their transformers. We don't have to worry about capacity issues in that county, as these would be able to be fully freestanding and, have the capacity to charge these vehicles that, they might have had to wait 3, 4, 5 years in order to get the electrical upgrade and infrastructure in order to do so. So why does this matter to you? The biggest thing is it is quick to install and easy to scale. It allows for the implementation of a fully unified DC fast charging system where it's currently not possible today. And with a solution that can quickly be deployed, managed, and controlled remotely, it bypasses the obstacles that we're currently struggling with on the US grid. Thank you guys for your attention, and my contact information is below. If you have any questions, don't hesitate to give me a call or shoot me an email.
All right, thanks, guys. Before we get too far, I just want to clarify some of the basics. So I know that EV charging is, there's some pretty standard nomenclature around, level 2, level 3. But wanted to direct this question at Sean. Like, what is the difference between AC and DC EV charging, and how does your offer fit into this discussion?
Yeah, very good question. Yeah, you have to look at two things. One is the input to the charger, and the second thing is the input to the vehicle from the charger. And there's a mix of AC and DC out there. Most chargers that are out there, AC level 2 chargers, are AC to the charger, and then they charge your vehicle AC. Other fast chargers are still pulling AC electricity and then to the charger, and then they convert it to DC and they do the conversion in the charger, and they charge the vehicle DC fast charging. For us, we actually connect to a DC grid. So our charger is DC powered, DC coupled, and we charge the vehicle DC. It actually eliminates the need to have that conversion technology in our charger, makes the products lower cost, and we charge the vehicles DC, which is highly efficient. In fact, Chris kind of touched on it, but charging a vehicle AC, you rely on the vehicle's own internal AC to DC converter, which is horribly inefficient. And we've seen anywhere from 10 to 20% energy losses in that conversion. So we are really focused on DC all the way around. DC input, DC output. And then we have the different level 1, level 2, level 3. Our chargers tend to be kind of in the level 2 range. So from the 5 to 25 kilowatt level. Beyond that, you get into the fast charging, which is then kind of defined as level 3. And all of that is going to be DC.
Awesome.
So let's go back to the previous slide, Daniel.
Oh, sure.
Just kind of talk about something. When we talk to a lot of fleet owners and operators, the story is always the same. It's like, okay, we're going to electrify our fleet. We're going to be ordering some electric vehicles, and so I don't know what to do. We need to get chargers in place, and that's the first thing that people think of. I need to get chargers because I don't want to take ownership of the vehicles and start enjoying the benefits of having an electrified fleet, which is lower cost maintenance. I'm not pulling vehicles out of operation to do tune-ups or oil changes and all the rest. So I want to get there quickly. However, while a lot of people end up kind of saying, okay, how do I get chargers in? You really should take a step back, because the chargers are only one aspect of the solution. You also want to look at, do I want to include clean energy generation and storage into the whole mix? Because that will, once you're in there kind of installing chargers and an infrastructure, you want to take advantage for the long haul. And so this is where you have to look at really the full picture of the DER that goes along with it. So, Daniel, next slide.
Yeah.
So our EV charger is a 20 kilowatt charger. As I mentioned, DC powered. We have adapted it to take on current hooks. So we use droop control. It's configurable. We handle all of the other aspects of current OS. And this was a product that we were running without current OS, and we have adapted it for current OS. So 700 volts, which is the current OS standard, and this is what we operate. Now, whenever we talk about, as I was mentioning, the capacity level, this is 20 kilowatt. We tend to orient this towards fleet operations. Fleets have their vehicles running all day long. They come back to the depot in the late afternoon, early evening. They have 10 to 12 hours to charge. And so this is the charger that ensures that they'll be able to have the vehicles fully charged by the morning. So we don't need the fast, ultra fast chargers for this kind of solution. We're looking at kind of the right purpose-built type of operation. And so again, low cost, efficient, and effective. Next slide. And this is also something that Chris touched on earlier. For a DC coupled infrastructure that we're talking about, we also see 30% lower CapEx costs. And that's if you really just are connecting to the grid. You don't have any other DER associated with it. So just, inverter that's creating a DC microgrid, and we're attaching our chargers to it, 30% lower CapEx costs. If you add in clean energy generation like solar panels, along with battery storage, we're seeing the same 50% lower CapEx costs. And it just has to do with with less components, materials, labor that gets associated with that, which oftentimes the labor is well more than the actual equipment costs. And then also, as Chris mentioned, the OpEx costs. Again, for AC level 2 chargers, which is really kind of what people tend to think when they're kind of doing something quick, even though it could take a year or 2 years to get in place. The inefficiencies that you get for AC level 2 charging are really significant. So by avoiding doing AC charging and avoiding that internal converter, you're going to save operations costs. And the way I kind of explain it to a lot of people is, if I'm a logistics company and I have a DC infrastructure charging system, and you're a logistics competitor and you have an AC, I am going to have 10 to 20% lower fuel costs, electricity, every day of the year. And that is going to provide a competitive advantage right off the bat. If I add more green energy to it, I'm even going to get bigger advantages with a DC system. Also, from a standpoint of installation, as was mentioned earlier, much faster, whether it's an off-grid solution, which can be very fast, or even on-grid, where you have an inverter that ends up insulating you from the grid. You had set up a DC microgrid. Even in those situations, well faster than AC. And in fact, all the permits, inspections, approvals, both from utility and local jurisdictions, they mount on the AC side, and it's just a simpler process for DC. So this is what we really focus on in terms of a DC infrastructure, and also allowing a scalability into the future, adding more chargers, adding more DER to the whole operation. And then also from a sustainability side, that's significant to us. This is kind of a diagram showing just the differences in AC versus DC. AC coupled system, you have multiple transformers, step-down transformers, which can be avoided in some cases with a DC by going straight to an inverter. They can take the higher voltage level, so you don't have to do a step-down transformer. And then all of the other operations. And again, if you're utilizing clean energy components like solar, batteries, wind, or even hydrogen generators, then you already have an inverter. You're already on the DC side of the system. Makes it much simpler to add things over time. And again, the efficiencies are just astounding. I'll also mention one other thing that Chris had mentioned, and that is the wiring. We see a significant improvement in less wiring, which we also look at as a sustainability aspect. For a 100 vehicle depot that we were involved in, it actually utilized 11,000 pounds less copper in that process. Again, we're trying to save the environment. We're trying to actually harvest as much clean energy as we can. Also being able to utilize less materials that are precious as well. That's also important. So my contact information, please reach out if you need anything.
Awesome.
Thank you, Daniel.
Thank you, Sean. So before we move on and open up for Q&A, just wanted to let people know at Current OS, we have in face-to-face, in-person meetings that we hold several times a year. Our next one is coming up September 30th through October 2nd. It will be in Cleveland, Ohio, and hosted at the Eaton facility there. If you'd have any interest in that event, please reach out to us at info@currentos.org. Now, we'll get to the questions in the chat. I just also wanted to kind of circle back around to Sean's last comment about material reduction. I think that those of us who have looked at the electrification of everything and the trends going along in that line, it's really crucial that we do things with the least amount of material as possible, as the amount of material reserves in this planet are a limited resource. So going to the chat here now, and I'm just going to go down in order. So Chris, thank you for kicking us off with a question about
you like that?
yes, other top applications, and we see Ritu is looking at EV charging with different applications. Would anybody like to address? I mean, we sort of focused on commercial fleet here, but are there any other thoughts from the panel on different applications?
Yeah, go ahead and take that and start up. We talk about fleet, but really when we talk about fleet, we're actually it's a broader sense, so multiple vehicles. So it doesn't necessarily have to be a company with 20 or 30 or 50 vehicles. It can also be office buildings, car parks, things like that, where individuals are going to be charging their vehicles. We focus on fleet because this is kind of the fastest moving electrification of vehicles, but as passenger vehicles come up, that's also going to be the next thing. The architecture, whether it's a fleet depot or whether it is a retail mall that is charging passenger vehicles, same architecture, all of the same principles apply, and the same cost savings.
Awesome. Thank you, Sean. Let's see. We also, Kareem has a question here directed towards the audience, but I'll ask the audience if you guys can chime in on chat. That would be fantastic. But the panelists we have today, the question is how to ramp up your production while your biggest supplier, i.e. inverters, is China. Any thoughts on that from the panelists?
So I don't know if I understand the question completely, but we talk about AC to DC conversion and then DC to DC conversion. When we us at like Schneider Electric, right? We talk about sourcing products that are produced whether in the U.S. or throughout North America, especially for projects where there's extra incentive for the federal tax credits. I think that's always something that we do and we always focus on. So I think there's a decent amount of AC to DC conversion that's in the U.S. market that doesn't have a large domestic or doesn't have large content from China origin.
Yeah, I'll second that with Chris. Our system is made in the United States. Not as much recently with the current administration, but I felt like there are a lot of module manufacturers that are now starting to be manufactured in the United States. I do think we have a long way to go to catch up to what China can do on the renewable energy space, but I think the U.S. has at least taken steps to narrow that gap over the last 5 years.
Yeah, let
Yeah,
me
and
also add. Let me also add that we our charger is manufactured in the U.S. as well, and that was a decision we made early on. What and I think it's broader than just inverters, but a lot of the inverters for the larger scale systems, they aren't necessarily built in China. Smaller inverters, solar inverters for residential like commercial, many of them are from China, but the larger ones, because we're talking about big boxes, they're manufactured in a number of places, Mexico, US, and some other places that are not China. So I think there's an improvement from the standpoint of getting non-China oriented products. So I think the production ramp, we're all, I think, pretty well aware of where to source from, and kind of we've been anticipating this for quite some time.
Thank you, Sean. I think Chris also alluded to in his segment that we've seen an increased uptick in manufacturing from onshoring, which is contributing to the increased demand. So I know that we've seen that here at Schneider Electric, and that's something we've recently announced, building a new plant on our El Paso campus to sort of address some of those concerns as well. I have a question, Daigu, I think, apologies if I mispronounce your name, but what type of challenges do you face when you implement DC solutions?
Well, I would say when we were looking into this, we were initially doing something more efficient, again, that exponential change and improvement, right? We talked to our colleagues in China, we talked to our colleagues in Europe, and that's where I learned about currentos. And that's where currentos really assisted us here in the US with these projects of creating that framework for the system architecture that we deployed. Otherwise, it was too difficult to try to figure out. I think that's kind of like even the question I think that I heard Sean answer about, why don't we have more DC distribution? Well, where do you start? And that's where currentos does a really nice job of creating that framework. And we saw a lot of benefits from it. So I think that's probably why we're starting to see it more and more now.
Yeah, I would echo that, and that the biggest challenge with that we face with DC solutions is getting people to understand it and realize that there are solutions with DC. As I said, we've kind of grown up in an AC world, and the first thing everybody always thinks about, okay, how do I wire things from an AC standpoint? But no, there are alternatives, and they're better alternatives, but it's not what people have been used to thinking about. Sorry, Travis.
Yeah, and onto that, I'd say as being more of a smaller company, a lot of our initial system was AC based with an inverter. And it was when we started teaming up with Schneider and currentos, that we saw the value add of moving towards a DC solution. And then as Sean said, there's still, when people think microgrid, they typically think this cannot be grid tied, where that is not the case. You can still have a DC solution and grid tied at the end, if that's something that you're looking to do. I think that's been a large challenge, trying to get people past that point.
That's an excellent point, Travis. And I think with the Raleigh project that operated in a grid island mode for 8 or 9 months before we were able to connect it to the utility there. So that's an excellent point, being able to run as a grid island and then integrate later when your time is up in the interconnection queue. Okay, a couple more questions coming online. We got one from Arthur. Current has any material standard recommendations on power quality applied in these systems? I think that there is. We have a design reference guide that current OS has developed for these applications that I think guides us. For those of you that may not be familiar to when the team talked about droop control, droop uses basically voltage drops and swells to manage the system. So that is sort of core to the current OS design reference guide. But I think if you reach out on the info@currentos.org email, we can foster a conversation that may dive a little bit deeper. I know personally when I do direct current codes and standards work, and we've been talking a lot about the differences between power quality and an AC paradigm versus the DC paradigm, and it's different. It's a completely the things that we worry about the most with power factor, harmonics, all of those sorts of issues, related frequency drop off with the AC world, and what we're concerned in the DC paradigm is a lot more focused. That's
we actually, from our projects, we actually had a really good experience using current OS to help stabilize a system. So traditionally, if you think of an AC system, we'd use a control to, you talked about balancing that frequency, but it's the grid itself has a lot of over voltage, under voltage conditions. It's really not that stable. So current OS really helps stabilize the different projects that we've deployed and provided us really nice power quality to meet those stability challenges.
All right. Kareem has a question in here. Following a recent conversation with someone involved with modernizing the U.S. electrical grid, the tradition from large distribution transformers to solid-state transformers prompted the response that copper and steel will always be cheaper than chips. What are people's takes on that statement? And I know that from my just reading that myself, I have some thoughts, but maybe we'll start with Chris and then move to Sean and Travis. If that works.
So I'd say, will a solid-state transformer will be more expensive than a traditional copper winding? Yeah, I think it's gonna be more expensive, but it's gonna be produced a lot faster, and then you can use that one model for maybe 34.5, 69 kV, delta, Y. So all these, where today you have to have a custom transformer for your system and for different voltage levels, where the solid state eliminates that. So now you have one model that you can use in those various applications that's able to produce a lot faster. So there's a significant value in the time saved and the flexibility.
Awesome. Thank you, Chris. Sean, thoughts?
Can't really speak to the aspect of the solid state transformers and distribute, but what I would say is that that comment seems typical from kind of a utility grid kind of a guy, but anyway, I spent a lot of my career in the computing industry, and I remember back in the days when we relied on magnetic media and hard drives, and it was always, there's no way that semiconductors will be able to catch up, so memory, and the reality was we tracked it, and it ended up replacing kind of the floppy drives first, then it was like my Omega zip drives next, then it was like hard drives. And I don't even know if there are any hard drives in existence right now. It's all solid state storage. So whenever somebody says that this will always be cheap, it's like, time goes, new technologies develop, and I could point out many situations like that I've seen. So, and by the way, I'm a believer that the grid is going to increase. There's going to be more copper used. There's going to be more transformers, and if you want to invest money, put it into those kind of companies, because there's still a lot of business to be had there. As we said earlier, the electric demands are going to go up 3x. I believe that. So that's my thoughts.
Yeah, good. Thank you, Sean. Travis, do you have any thoughts on the topic?
No, I think they're more applicable to that. And I thought you guys both had great answers.
Awesome, thank you. And I guess I'll throw my own answer out there, and that from someone who's spent some time in a transformer manufacturing plant, the thing that we're missing is the very manual nature of winding a transformer is associated with a human resource cost, right? And so, as we look towards solid state, I don't know if we'll always be cheaper, but copper and steel are also commodities that have pricing volatility implied in it as well. So if you want to try to take advantage of lower human resource costs, now you're adding in a transportation leg into the cost of the unit economics. So it's a complicated question, but I tend to agree with Sean and his hypothesis of a Moore's law parallel.
Yeah, that's a good question.
Okay, Gary.
There was on that
Yeah.
topic. There was actually a recent IEEE article on solid state transformers, and about how we're going to see that as the predominant technology being deployed for the U.S. grid as it modernizes. Maybe a month or two ago.
Interesting. Thank you, Chris.
Yep.
Gary, okay, we've been manufacturing and installing carport structures for over 40 years. And as we begin to integrate EV chargers into our comprehensive carport and solar projects, we're particularly interested in the potential of DC fast charging. He has two questions. Do you see hybrid models as viable, specifically using DC fast chargers while also converting DC to AC to help offset on-site electrical usage? So maybe we'll start there, and maybe we'll go backwards on this one. Travis, start with you.
Yeah. So I think Sean made one good point about this is not every one of our systems is meant specifically for some massive electric fleet. The bulk of the installations that we have done have been at, country clubs, malls, scenarios where people are looking to pull up, park for a short portion of time, do whatever they need to in the real world, whether it's golf, go to a movie, do some shopping. I think this would be a huge asset for a lot of the hybrid models that they don't need the 150 kilowatt fast DC charging. If you bring in, one of like Sean's EV chargers that can get, 12 to 25 kilowatt hours, they're still able to shop at the mall for an hour and fully charge their vehicle while they're there. And then the benefit we'll use the mall as an example, it's a way to bring customers in, and then any of the extra energy can be run back to the grid to offset their utility cost. So it really is a win-win for the business looking to implement something like this. And then I guess to your second question, World for Solar, we are the OEM. We typically do not install the systems ourselves. So we usually are teaming up with builders, solar installers, etc., where they might have some specific project that they're looking to implement our hardware. So there are multiple scenarios where we'd be willing to work to implement our product into real world applications.
Yeah, and on that second part there, Travis, I think that you really hit the nail on the head, in that we have sort of a learning curve that working with installers, we can accelerate the installation time. I think the first time you see a DC application, there's a lot of questions, but as deployment tends to grow, the benefits would increase from having that partnership between the manufacturer and installer. Sean, did you want to add? Chris, did you want to add anything to the second set of questions?
Travis had a great response.
Awesome. All right, Andres, how much of the existing AC infrastructure could be used for DC as well? Oh, that is an excellent question. I will defer to my panelists for initial thoughts.
Yeah, so I think the question is, like, if there's AC wiring, could it be used? So, we've seen instances where the AC wiring was rated enough where we can use that same conduit, that same cable, and then apply DC power to it, DC current to it. So, it depends on the rating and the insulation level of that cable.
Yeah. and I would agree. It's like it could be used. I mean, it all depends on kind of the topology and things like that. But yeah, AC an AC infrastructure tends to have wiring that is heavier gauge than what DC requires. So yeah, it might be wasted, but you could potentially utilize a lot of that for a DC implementation.
Awesome. Yeah, I know, Chris, you had shared with me an instance at a Nashville manufacturer whereby they were looking at a project
Yep.
and the existing AC infrastructure would be redeployed in a DC solution, and that had a pretty good upside. Can you speak about that a little bit, maybe?
Yeah, that's a good example. So that was a project where they were upgrading existing chargers and solar that was probably almost 20 years old, like definitely first generation equipment. And the thought was putting in new solar, putting in it wasn't that many chargers, maybe like 8 chargers. But when you look at replacing all that, you're putting newer chargers and newer modules, higher wattage, more current. So you got to replace all the wire and the conduit. Super expensive. I mean, just to give you, I remember that specific project, including that with the switchgear upgrade, was 1.4 million US dollars, right, for that. And it was, it's a couple thousand feet. And you look at it doing DC, you don't have to upgrade the switchgear. You can use the same breaker that's in there. And the insulation level was high enough in that cabling, and so we didn't have to replace the cabling. We didn't need to install additional conduits. We could use that one conduit that was already run. It was a $1.4 million savings for, and it wasn't that, it was a pretty small project. But that's a huge savings to them to be able to reuse that infrastructure.
Yeah, and I think that what's implied really in that lesson is that these DC grid islands or DC interconnected microgrids have the ability to open up the options that are on the table. A location that might otherwise, I know that I've walked a lot of job sites with customers looking at projects on the front end, and you sort of come to that decision tree of what's accessible. Where can I put this is largely dependent on where things already are. So the question about existing AC infrastructure, that it's valuable to be able to interconnect there, but having a DC island may put an option on the table that didn't exist before. I also think that a lot of the utility factors drive some of this conversation. So if you're trying to take advantage of a utility infrastructure rate, then how you segregate your loads may be important, right? Whereas the project we spotlighted during this webinar, we're connecting that directly to our building loads and using the charging infrastructure to help supplement the building load. So we're extracting value out of that solution and to the point where it makes sense. But every project is an independent project, and things will vary state to state, utility to utility, and giant oak tree to giant oak tree. Let's see. I'm not seeing any new questions in the chat, so we're a minute away from our advertised close time. So I'm going to call that a success and thank my panelists. So thank you, Chris. Thank you, Travis. Thank you, Sean. Really appreciate the time that you guys have put behind this. And then also Prashant and Rafael, thank you for helping us coordinate this with the Current OS Foundation. Appreciate your help on that as well. So at this time, we'll adjourn, and thank you all to the audience for attending.
Thanks for having me. Thanks for moderating.
Thank you, guys. Yeah, appreciate it.